So let's take a look at this problem here. We're at 1000 Kelvin. The equilibrium constant is 0.021, and the initial concentration of carbon dioxide is 0.012. And it says calculate the equilibrium concentration of carbon monoxide. So CO2 is a reactant. Graphite is also a reactant, but it's not applicable because it's a solid. Carbon monoxide is the product we're looking for at equilibrium. So we write the equilibrium constant, CO squared over carbon dioxide, ignoring the solid graphite in the equilibrium constant expression. And we set up the ICE table, and we subtract some amount from CO2, and stoichiometrically there'll be 2x added to the right side of the equation, or 2x will be added to the CO concentration. That 2-to-1 ratio is reflected in the 2x. And at equilibrium, we use these expressions here, 0.012 minus x and 2x. And we substitute these expressions into the equilibrium constant expression, making sure that we're squaring the 2x. And remember that squared came from the coefficient of 2 in front of the CO. And now we could simplify our math and ignore this minus x in the denominator, perhaps. In other words, is the forward direction, or is the amount of product produced negligible enough to cause a significant or reasonable difference or loss in the initial concentration of CO2? Well, the equilibrium constant is kind of small, and you say, well, it's probably not going to produce that much product. But we're going to use this criteria to see if we could actually ignore that small change, or if that change is small enough that we could ignore that minus x in the denominator. The question is the initial concentration of, in this case, the reactant, greater than 100 times the equilibrium constant? And it is not. So because of that, we cannot ignore x. So the loss of the CO2 is going to be significant enough that if we were to ignore it, it would cause an error in our solution. So we need to keep that x in the denominator, that minus x in the denominator. So that complicates the math a little bit, and so we have to go through and set up a quadratic equation and determine a, b, and c. And then if you plug this into a quadratic formula, you'll get the reasonable or acceptable answer for x as 0.00574. Remember, there are two answers that you get from the quadratic. One is unreasonable. It's either negative or way too big. And then you get the correct answer. So that's x. That's not your final answer. So that x is the loss in the CO2. But 2x is the equilibrium concentration of CO, and that's what we're after. So we multiply that value of x times 2, and we get 0.11 approximately. In this problem, we're given the equilibrium concentrations of 2 of the species and asked to determine the equilibrium concentration of one of the products, the CCl4 carbon tetrachloride. So in the ICE table, we complete the bottom line, the equilibrium line, and we have the equilibrium concentrations of the reactant and one of the products, and our unknown is the CCl4, so we put an x there. And it is 1x, or just x, not 2x or anything else, because the stoichiometry for the CCl4 is simply 1 CCl4. So we set up the equilibrium constant expression and substitute the equilibrium values that we know, and making sure we include that squared for the reactant, and then proceed and substitute in the numbers. And this is pretty straightforward, solving for CCl4, making sure we square this number. and we get 0.0273 for the product carbon tetrachloride, or CCl4. In this problem we have two species, I2 and I, and we're given the initial concentration of the reactant I2 and asked to determine the equilibrium concentrations of both of these. And the stoichiometry here is 1 to 2, so that needs to be reflected in our ICE table. So we subtract X some amount from I2, the reactant, and then we add 2X to the product. Show the equilibrium expressions in this line here. So that's 0.00854, the initial concentration, minus some amount X. And then we have 2X for the product. Then we set up the equilibrium constant expression, I squared, don't forget that too. And then dividing that, of course, by I2. Then we substitute the equilibrium terms into the equilibrium constant expression, and 2x squared, so that means we end up with 4x squared. And the denominator includes a minus x, and we ask that question again, is this loss of x negligible? In other words, can we just ignore it and simplify our math? And the equilibrium constant is pretty small, meaning there wouldn't be a lot of product produced, so there wouldn't be a great loss. We would hope to think there wouldn't be a great loss of reactant. But we start off with a pretty small initial concentration of reactant. We need to consider this, even though it might be small, the small change or the small loss from our initial concentration. And to determine or to verify that we're going to need to include this minus x, we ask that question, is the initial concentration of the reactant greater than 100 times the equilibrium constant? And the answer is no. So we proceed setting up the equation here in terms of a quadratic, and we determine A, B, and C, and we solve for the x values using the quadratic formula. The answer that is reasonable from the quadratic formula is 0.00240. So at equilibrium, I2 is the initial concentration minus the value of x. And then the equilibrium concentration of I, the iodine, is simply 2 times x. So remember, once you get x, that may not necessarily be the answer you want to report. You have to go back and look at the E line, the equilibrium line, and see how that x was expressed in this. In this problem, we are given initial concentrations of two reactants and asked to determine the equilibrium concentrations of all species. And the stoichiometry here is 1 to 1 for the two reactants, but the product has a 2 in front of it, so we have to take that into account in our ICE table. So we show the initial concentrations of the reactants, starting with 0 concentration of the product. There is loss, of course, of the reactants and gain of products, and the stoichiometry needs to be reflected in this line. 2x for the product. Then we carry down the terms from the I and the C lines, showing the equilibrium concentration terms, 0.08 minus x and 0.02 minus x, and then 2x. And we plug these terms into the equilibrium constant expression, and it looks pretty daunting because we have a minus x in both of the terms in the denominator. And we ask that question, is the initial concentration, well, in this case of both reactants, are those concentrations greater than 100 times the equilibrium constant? And the answer is yes. So that means we could ignore this change or the loss of the amount of each reactant. So we drop the minus x terms, and it really simplifies the expression nicely. And so now we're left with just this squared term in the numerator. And then we solve for x. And now x is 6.3 times 10 to the minus fifth. Now remember, again, that x may not be the answer you want to report. You have to go back and you need to go back and look at your equilibrium line in your ICE table and find out how x was used here. So x was subtracted from these initial concentration, then it was multiplied by 2 for the product. And that's how you want to use x in your final answers. Here we have a similar problem where we need to determine the equilibrium concentrations of all the species. And we are given the initial concentration of the reactant, and we proceed setting up the equilibrium constant expression and discover that we cannot ignore the x in the denominator. In other words, that loss of reactant as equilibrium is attained. So we proceed and set up a quadratic equation and then use the quadratic formula to solve for x. And the value of x is 0.0224. And the answers we want to report are 0.0250 minus x, because that's the equilibrium concentration expression for the reactant. And in this case, the x is the concentration for both of the products. Here are some problems that you could try to solve on your own. I provided the answers.